All right, so welcome back. I'll talk to you about 5G, and the idea is I'll walk you through the history of cellular communications, how we came to 5G, what it promises, what reality is, and what we can expect in the future. Right? So let's start with a historical tour of things. So if you think about wireless communications, roughly about 150 years ago, James Maxwell predicted the existence of radio waves. And then Heinrich Hertz, he demonstrated that radio waves can be generated. And then, depending upon whether you're an Italian or an Indian or a Russian, you would say whether Marconi or Bose or Popov came up with the first wireless communication demonstration. And then in the early 1900s, countries started doing broadcasting of radio communications. And these were mainly, entertainment and news and so on. And with the advent of World War II and so on, that's where the first portable AM radios came up, right? And then in the 70s, the first technology for private phones, personal phones was demonstrated and so on. So let me just walk you quickly through this. Right? This is the first portable AM radio, amplitude modulation radio, developed by the US Army. And this is, the range is about 7 kilometers, let's say, and it weighs 10 kilograms. So imagine you carrying a big bag of rice with you, and that's how you make your phone call. And this is where the first prototype of a mobile phone. This is 1973, and this was developed by Motorola. And the gentleman you see in the picture here is Martin Cooper. And back then there were these. So one of the biggest organizations doing research in wireless communications and networks is to be called Bell Labs, right? And Bell Labs and Motorola in this case were rivals. And in this particular race was won by Motorola. And here you see Martin Cooper making a call to Joel Engel, who was his rival at Bell Labs and also trying to do the same thing, right? So Motorola won here. But then that was just a prototype demonstration, right? Commercial deployments, commercial mobile phones didn't become available till the early 80s. And this is one of the first mobile phones which came out, and this is from Nokia. And this again weighs 22 pounds, which is roughly about 10 kilograms and so on, right? And this is what started what we call the first generation of mobile phones or cellular networks. And thinking about, if you're familiar with communications, so the first generation of mobile phones is what we call analog, right? So the transmissions and so on here were analog. And as a result, the data rates were low, the capacity of the network was low and so on. Another handset, this is from Motorola, so right, and then this is 1983, much lighter, about 2 pounds, which is a bit more than a bit less than a kilogram, I guess. And in today's money, costs about $9,000, right? The second generation was in the early 1990s, and in this case, the biggest jump was that we moved from a completely analog system to a digital system, right? And one of the acronyms you may have heard is called GSM, and that's where the whole thing started. And this is your example of an early 2G phone. This is Motorola. And then, the clamshell phone came out in about 1996. And if you're a science fiction fan, you may have seen Star Trek, the original series, which was in the 60s or 50s maybe, Captain Kirk would flip open a thing and then he would communicate, and they say that this was kind of inspired by that design. And then, Nokia 9000 communicator is sort of the first smartphone in the sense that it had sufficiently good communication capabilities. 3G came out in the mid 2000s or early 2000s, and the first one here to run Windows was something by Palm. I had something like this back then, and I was primarily using it for GPS. Now we use our phone to watch videos, listening to music and so on. The Motorola Rocker E1 was the first one that could store music, about 100 songs, and that was the limit. And then things changed when Steve Jobs introduced the iPhone. That was 2007, right? And in many ways, iPhone is the precursor to the smartphone that we know of today. 4G, 5G. I don't see much difference except that in the 5G case, the screen seems to have gone all the way and the button seems to have disappeared from the first, right? So this is sort of, if you look at it from the handset point of view. But what about technologically, right? What has changed? So I'll walk you through with a chart with a chronological thing. So 1G came out in early 80s, and you could only do voice. You could only make phone calls on this, and things were analog, and the protocol was called AMPS. 2G came out early 90s, and we don't always just go in integers. We like to play with fractional numbers also. There was 2.5G, 3.5G, and so on. But the biggest thing here was that now, in addition to voice, you could send out SMS, short messaging services. You could send out small things. And now CDMA and GSM were protocols, and then 2.5G extended it to GPRS and so on. With somewhere between 2.5G and 3G, we introduced data. So now you could also browse the web, but the data rates were very, very low. 3.5G in the mid-2000s tried to enhance that, and now, in order to just browsing web pages, now you could also look at multimedia. Maybe you could watch videos at very low resolution and things like that. And with 4G, you have mobile broadband. Now you can, things are much better. You can watch YouTube while you're on the bus or on the train. And now we are in the era of 5G. And one of the things that we say is now everything in the world will be connected, including non-living things and back to like 4G or other things. If you think about communication, at least on one side, there's a human being. It's me who initiates a call, me who uploads a video on YouTube. Now, with the Internet of Things, there doesn't have to be any human involved. Machines are intelligent enough to know when to start and transfer data and so on. Now, let's look at 5G in a little bit more detail, right? What does 5G promise? If I start at the very top, one thing is that now 5G networks are supposed to be able to handle a lot more devices, right? There are 7-point-some billion people in the world, but with 5G, we talk about 500 billion devices to be connected. So essentially, we're not talking humans anymore. Now machines will also be connected. But for you and I, probably what's more interesting is that 10 Gbps number, right? We all want high data rates, right? I don't want to wait for my things to buffer. I want to download a movie in 2 seconds. So that's where the 10 Gbps comes in, which is, if you have kept track of how quickly you download data with your LTE or 4G connection, that's about 100 times faster, right? Or maybe even 1,000 times faster in some cases. And 5G networks are expected to carry 1,000 times more data. And for low-powered IoT devices, you put in a battery once, and if you're using 5G, they will take so little energy that they can last for 10 years. And then the last thing there is the latency. For many applications such as self-driving cars and so on, they need to make decisions very quickly. So you cannot wait very long, and they need to hear from the network. They need the network to process the data for them very quickly, and that's where that latency comes in. 5G promises you 10 milliseconds. Okay, in a little bit, I'll compare that with 4G. In terms of what 5G gives you for applications, we usually break the 5G applications into 3 parts. At the very bottom on your, left-hand side, you'll see that MMTC, massive machine type communications. Those are supposed to be for your IoT devices, small devices sending a little bit of data. But if you go up the triangle, you see eMMBB, which is enhanced mobile broadband. That's for you and I. Our phones, maybe we, in the future, maybe we can even get rid of the cable connection or the optical fiber coming to your home. You don't need that anymore because you can just connect everything to 5G and you'll get just as good data rates or even better. And at the very right-hand bottom corner of the triangle, you see URLLC, or ultra reliable low latency communications. And these are for things such as industrial control, self-driving cars, and so on. And here the idea is, if you're trying to control a chemical plant over the internet, over the network, you don't want any of your data to be lost, right? You're trying to control the temperature of a nuclear reactor, maybe. You don't want any packet to be lost. You don't want controls to be delayed, right? If your self-driving car gets the signal to brake a little bit lower, most likely it's going to have an accident, right? So we are looking at very, very low latency and very, very high reliability. So this is sort of how we demarcate 5G applications, right? So now let's talk about that thing at the top, eMBB, which wants this about 10 Gbps data rates, right? So how do we get to this 10 Gbps data rate in 5G, right? What's going to give? So in order to understand that, then we think about, one of the most famous persons who sort of dictates how we do wireless communications, Claude Shannon, again, Bell Labs guy. Shannon says that if you want to have data rates, high data rates, you can do two things. One is you can increase your bandwidth, right? And the other is you can have higher signal to noise ratio. So let's talk about increasing the bandwidth, right? So how do we increase the bandwidth? Basically, you go to your government, right? IMDA here in Singapore, and you tell them that I want more spectrum. I'm willing to pay money, give me more spectrum. Then IMDA looks through. This is a very intense picture, but this shows the entire Singapore spectrum. So IMDA says, all right, where are things available? Maybe that's what I can give you, so you have more bandwidth to transmit on. If you look at these red circles that I've pointed out here, these are the frequency bands where Single, StarHub, and M1 transmit right now. They are either less than 1 gigahertz, and we have some about 2.1 gigahertz and so on. So most of the top rows are the lower frequencies, and you can see that they're all occupied. So, for example, your FM radio transmissions go there. When Changi Airport wants to do air traffic control, it goes there. Singapore Air Force, Navy, whatever, they communicate in certain frequencies. So there's nothing left, essentially, at the good frequencies. So what is left? You see those zebra-like slanted black and white things? Those are the unallocated ones. They are at very high frequency bands, and and if you think about in terms of their wavelengths, they're in the millimeter wavelength band. So those are the ones that are available. And if you want to have high data rates with 5G, that's where Single, StarHub, M1 have to go and ask the government for opening up those frequencies. And actually, the IMD has opened up, and I think Singtel is going to transmit at 28 gigahertz. That's one of the things. So these are the ones that it will transmit. Right? So that's one part, and these are some of the enabling technologies for 5G. So we have to transmit at higher frequency bands, and that's where this millimeter wave communication system comes in when we are talking more than 20, 30 gigahertz. It's good. You have lots of empty space there. You can transmit, but then, nothing comes for free. And the problem here is that the propagation characteristics of radio waves in these frequencies are very bad. So at lower frequencies, you can set up a cellular base station here, and you can hear it maybe 5 kilometers, 10 kilometers away, right? But with millimeter wave, if I put a base station here, it'll go only a few hundred meters. And it's not going to cross walls. If it's raining outside, your millimeter wave will not go. Thankfully, we don't have snow in Singapore, so that's not a problem. But in colder countries, if it's snowing outside, it doesn't work. Right? So millimeter wave can do certain things for us, but also there are issues. And then when I was talking about Shannon's law, I said bandwidth, and the other is signal to noise ratio. Right? So one effective way of improving that is through fancier ways of doing channel coding. And 5G will use some newer forms of LDPC codes, low density parity check codes. The other thing that 5G will enhance is something called network slicing. So what's network slicing? Single, StarHub, M1, they own the core of the network, right? From the moment that the data leaves your phone or your laptop or your computer, it enters one of these three networks, and then they own the infrastructure. So imagine that you are sharing that infrastructure with every other Single or StarHub or M1 customer. There are humans, there are machines, everybody is sharing the same. So as a result, things may not, so I may want higher data rate, but things may not be available in the network for me. With network slicing, what we do is we keep aside portions of the network resources based on how much you're willing to pay, always comes to money, and also what your requirements are, right? So that's something which is possible. And then the other thing is, which will come with 5G, is massive Mimo, right? So this is my phone here, and we can imagine that it has an antenna inside, right? It has actually multiple antennas, one for Wi-Fi, one for 3G, 4G. Actually, this is a 5G-enabled phone, but I don't know if I'll ever use it or not, but anyway. So it has antennas for all of those. But just for, so right now, if I were on data plan, I would be on a 4G network here from Faculty of Engineering in NUS. So for that, this phone has 4 antennas inside. We don't see it because it's inside the cover, but it has 4, not 1 antenna. And with 5G, we expect that to go to maybe 24, maybe 16, maybe 32, maybe 64, and so on. And similarly, if you ever look up a cellular network base station tower, you'll see many antennas on top. And actually, if you ever come to NUS engineering, come to Faculty of Engineering, right, and look up the top. There are many cellular base stations on top, and you'll see antennas protruding in different ways. But with 5G, the number of antennas in a base station can potentially go up to 1024, 2048, and so on. So large. And the reason we do this is because it helps with our communications, and we can get higher data rates and so on. Other things 5G will focus on will be massive connectivity for IoT. Remember the 500 billion devices I was talking about? And it's not easy to support them. And traditionally, if you look at how cellular networks work, if I want to send any data or I want to make a phone call using this guy, first this will send a request to the base station. Base station will send that request to the core of the network. Then some grant will come back. Then I will send data. For an IoT device that, I can go back home and charge this thing. An IoT device you cannot charge. You're not going to come and replace the batteries. So those things are very wasteful. So there are protocol enhancements coming up in 5G, which says, if a machine wants, if an IoT device wants to send data, it should be able to do it very, very quickly with very little overhead, right? And then there are other things. For example, this is more from the network protocol side of things, where they're trying to enhance TCP, the transmission control protocol, so that it can better utilize the resources, and the data rates will be higher and so on. Right? So these are 6 sort of key enabling technologies that will go into IoT, and it spans more all the way from microwave and RF, communications, networking, coding, and the whole thing. Oops, sorry. And there are other things that are coming up, and so RAN stands for Radio Access Network. So some of the things in the new air interface, Mimo, millimeter wave, beamforming, those are things we talked about. There are some other innovations coming up in the radio access network. So for example, my phone should be able to connect to multiple networks at the same time. That's your comp. And then the other big thing which will come up in 5G is right now when Synctel or StarHub deploys a base station, cellular base station, at least they expect a radius of a few kilometers to be covered with that, right? But remember how I was talking about millimeter wave, and then that doesn't, the millimeter wave will not cross through the walls. So how do we do that? So essentially that will mean is every room, every floor will have to have its own base station. So the cell of a cellular network, rather than being a few kilometers wide, will now be a few tens or hundreds of meters wide. So it has 2 implications. One is, now, if you are able to deploy that, it's like putting up a Wi-Fi access point in every room, right? We are familiar with that. Now with cellular, we are sort of moving there. We'll have a cellular base station in every room. Now it'll give you high data rates, but your cost will also go up, right? Because the base stations don't come cheap. And then there are other things like separating this management layer from the mobility layer and all those things. There are some other innovations that are happening in 5G, right? So if you think of a base station, so your phone or my phone connects to a Synctel or StarHub base station, and that base station actually costs a few tens of $1,000s. It's a very smart, complicated piece of machine. The wireless signals that I sent from my phone, they're all being processed, demodulated, decoded at that base station. But then, that also adds to the cost. So going forward, what we think is that, with 5G, our base stations will just be an antenna. That's it. They just receive the signal, but they don't do any of the processing. So who does the processing? It's like everything will be done in the cloud. So Synctel, StarHub, M1, they will have their own cloud. So they'll have their own cloud nodes. And let's say all the base stations around Clementi or West Coast area, their signals will be carried over an optical fiber to this one single computer. And that will do the processing for all the base stations around this neighborhood. Okay? So that simplifies from the cost point of view, but also complicates other things. But anyway, that's what your Cloud RAN is. Other things, we would be relying more on software-defined networking and network function virtualization. What we were talking about earlier was, when we have applications that need very, very low latency, for example, autonomous vehicles. If these guys are generating data that needs to be processed, and then they want feedback quickly, we are talking in the order of a few milliseconds. Right? Now at Singapore, we are very, very lucky in the sense that most of these big players such as Google, Amazon, and Microsoft, they have built data centers within Singapore. So if you look up how long it takes for you sitting, let's say, in NUS and trying to go to Google's cloud, my guess is if you try, depends on the time of the day and other things. If you try it after midnight, it'll be quicker. Now it'll probably a bit longer. It's about 15, 20 milliseconds, maybe somewhere about that. For certain applications, that's okay. But for some very, very real-time applications, that still may not be okay, right? So what you would like to do is you don't want your data to go across the network and then into the cloud. Rather, you would want to bring the cloud closer to you, right? And that's the concept of a mobile edge networking, where the idea is that instead of the cloud servers being far away, you bring computing facilities and put them where your base stations are. So essentially, your base stations also become cloud servers, and then you run your applications there, and your latency is much lower. And then we also split the control plane from the user plane and so on, right? So here's a matrix that shows you how different technologies that we have will either help us or hinder what the things that we're looking at. So on each row is one of those, like low latency, reliability, how many connections, and so on. And the columns show us what are the different technologies that can be used to achieve those. But what I would like you to pay attention is at the very bottom, which says reduction in TCO, right? That's the cost of operation. So what I'm trying to highlight here is that we can have different technologies that allow us to, achieve the objectives which 5G wants to achieve, but then they also come at a cost, and that plays out how 5G will be rolled out and deployed and so on. Right? So then let's look at what we expect in terms of the rollout of 5G. So right now we have 3G, 4G, 2G probably doesn't exist in Singapore anymore. So how will we do the actual transition from, let's say, 3G, 4G up to 5G? So there are two main architectures in 5G as far as rollout is concerned. One is called standalone, and the other is non-standalone, right? So let me walk you through this. So today we have 4G, right? So we have 4G networks everywhere, single star of M1. And here's a 4G base station. And that EPC thing that you see there, that's the evolved packet code. That's the core of the network. So let's say if I now come in, my phone, this existing phone, what it'll do is it'll connect to the 4G base station, and then it'll go to the network. So now if I want to deploy 5G here, what I need to do at the very basic minimum, I need to set up a 5G base station. That's easy enough. But then the core of the network, the laying of fibers, the interconnecting of the switches and so on, that's very, very expensive. So a telco would not want to put in billions of dollars on day one, or they may not even have the liquidity on day one to put in this kind of resources. So in the early deployment, which is what we call the non-standalone deployment, your phone will connect to the 5G base station, but then the base station in turn will be using the 4G infrastructure to actually carry your data. Right? So that's your non-standalone, and this will allow us to evolve gradually without sinking in too much money up front. Right? But as we go on, the 5G core will come up, and later on, 5G base stations can directly talk to 5G core, and that's the 5G standalone version of things. Let's look at some of the use cases for 5G. So, we have virtual reality and augmented reality, and the higher data rates you give me, the better my experience would be, and so on. We can also have use cases in healthcare, where 5G technologies will generally help in the well-being of the population. It'll let patients recover from their ailments in a little bit better. It will also enable things such as mobile surgery and remote surgery and so on. But if you look at what we are expecting from the network in this case, what we are expecting is ultra reliable, low latency kind of services, especially with remote surgery and so on. And then there's also another use case, which is smart transportation, which I was talking about. And in this case, 5G with its low latency, with its mobile edge computing will help things like autonomous vehicles and so on. So now let's compare 4G and 5G in terms of speed. While 4G can give us 150, 5G can give us, at least 100 times higher. Latency is 10 times or 50 times lower. But if you look at the spectrum, 4G operates at much lower spectrums, but with 5G, we can go up to millimeter wave. Battery life can be much higher with 5G. Data volumes will be 1,000 times higher, and so on. Right? But then the problem is that there are higher costs associated with this, with 5G networks. But this is all on paper. 5G promises you all of these things. But as a consumer, do I really expect that in the first place, right? So now maybe we can spend the rest of our time talking about that. In reality, life is very complex. The kind of performance that you will get from 5G depends on which frequency band your operator is working on, right? And we talked earlier about limited availability of spectrum. And if you are operating at below 1 gigahertz, things are good in the sense that your signals can propagate further and so on. But the problem is there's hardly any spectrum there, right? And you cannot get very high data rates. Between 1 to 6 gigahertz, it's somewhere in the middle. Your signals can propagate, but then they don't penetrate buildings so well, but your data rates can be higher. And this is the millimeter wave thing that we were talking about, much higher data rates, but then the coverage is smaller, right? And another way of looking at the same thing is through this. If you look at coverage, at the lower bands, you can go up to many tens of kilometers. But at the millimeter wave, maybe one room, or if you're lucky, maybe a few hundred meters. On the other hand, bandwidth is much higher at the higher data rates. We have lots of spectrum available. And they can also give you low latency. Right? So now, what is the exact performance that you will get? It depends then which particular frequency band your telco is using, right? And most likely they will use all three of them. So it really depends on where you are right now standing and trying to access the network. So you cannot expect to get the same performance everywhere. And if I walk back to the three service classes that I was talking about earlier, we had the IoT ones, we had the ultra reliable, low latency one, and we had the EMBB, which is the high data rate for phones and homes. If you look at the high data rate case, the use cases are cell phones and tablets. We want very high data rates. We have to have lots of devices. But then if for whatever reason, maybe you are somewhere where there is no small cell, you should not be expecting anything more than 50 Mbps, right? If you're somewhere in the middle frequency band, you will get something higher. And only when you are in a small cell with millimeter wave, that's when you will get the actual promise of 5G. And similar things with URLLC. The kind of low latency that it promises, you will only get when you're on premise. As soon as you leave your factory, if you take your devices or equipment outside, and if it needs to be outside, you're not going to get similar performance. And mostly it's on premise, and latency is again one way. So that if you need two-way latency, that's much poor. But on the good thing is this 5G is going to be much more reliable than 4G. And similarly, if you look at the last one, which is the IoT use case, here we have all these things that we wanted, right? We wanted low power, wide area access. We wanted a high battery life, big density, and so on. But reality is that we are not there yet. The standardization part of IoT for 5G is still underway, and we are not settled down on that. And currently, 5G is not optimized for small packets and very short sessions, right? It's still aiming at downloading videos and high data rate applications and so on. So there are lots of inefficiencies, and so we are still a bit far away. So I gave you the bad news, but what can we expect to improve? So as long as you have those small cells and picocells with millimeter wave, your performance will definitely, it's bound to increase. And you're going to get very, very high data rate at on-premise connections. For example, if you're at a mall or in a stadium, you'll get pretty good, factories and so on. And we will definitely get higher density connections, and security will also be higher. But at least for the time being, we cannot expect things like augmented reality at home, remote surgery, and so on because of speed and latency issues. Right? And much of the problems with 5G comes because of its reliance on millimeter wave. And the problems with this is that they don't propagate so well. They actually consume a lot of energy, and for the younger generation out there, you're you care about the planet and saving it, and 5G base stations tend to consume much higher power than your 4G and so on. And then the other issue with 5G is about security. No matter which layer you look at, we can launch attacks on the phones themselves. We can launch attacks on the base stations. We can launch attacks on the links between the base stations and the cloud and on the core and everywhere. Right? So security is going to be a big challenge in 5G. So when will we really get our 5G? Right? So let's look at history. And this chart sort of shows you, the peak of 2G, 3G, and 4G. And for all of these technologies, from the day they were launched and the day till they become obsolete, usually about 20 years. Right? And the peak comes after 10 years. So just as an example, if you see the first 4G phone was launched somewhere roughly about 2010-ish, 2009, 2010, let's say. And we are right now reaching the peak of 4G. This shows you how many handsets are sold every year. And 5G has just started in 2019, I guess, if I remember. Right? And the peak will come maybe in 5 years, 6 years. And so that's the expectation. And what will get us there? Ultimately, with all of this, it's all about money and whether the telcos will be financially viable while selling you these 5G services. Right? And right now, what they're really looking for are killer applications in order to get them there. Some examples could be, from a consumer point of view, you can have industrial point of view and so on. From a consumer point of view, some of these applications could be, cloud gaming, streaming of video, broadcast, and so on, where we want higher data rates and low latency. That's the selling point of 5G. And actually, some of the operators in different countries have already started doing that. And they are really aiming, most of the initial deployments are aiming at people who are into gaming. Right? So, all right, so hopefully I gave you some idea about what 5G is all about and the whole journey towards 5G and the promise of 5G. And just to conclude, 5G has a lot of potential in terms of giving us high bandwidth, ultra reliability, low latency, and so on. But before we get there, we still have to overcome quite a bit of challenges, and many of them are coming because of its reliance on millimeter wave, and then the fact that it adds to cost. And right now, we are still waiting for that killer application for 5G. Okay. So thank you all very much, and I'll open up for any questions. All right, so I see some questions on the screen. Somebody's asking, will we run out of bandwidth one day? All right. Yeah, my answer is, this is I don't know if I'll see it in my lifetime or not, but then, there's this whole thing about the CEO of Intel, and even I think Bill Gates at some point, they say, 8 MB or 16 MB is good enough for everybody, and we'll never run out of memory or whatever it is. But the answer to any such question is that yes, we will probably run out of things one day, and depends on what kind of applications come up. But the thing is, as soon as you give the resources or you come up with networks that are capable of carrying higher data rates, people come up with applications that will use those data rates. So it's a cat and mouse game, and I think at some point, since the spectrum is limited, at some point we will run out. All right, so the second question says, who would benefit the most from 5G implementation in Singapore? Would some companies be displaced or disrupted? So, all right, so I think maybe consumers like you and I, it's still a little bit to go before we start really needing 5G, And maybe people who are into watching, people who are into AR, VR kind of applications, or you want to watch your video in really, really good quality, maybe for you, you will need that. That's coming soon. But at least the initial use cases for 5G or the business cases for 5G would come from the industry. And in most cases, they would come from industry that are trying to go into automated services, or they're trying to automate their processes. And, for them, they might require things like high reliability, low latency, and so on. Right? So those are the companies that would go there. So now, would some companies be displaced or disrupted? I can't say about displaced, but definitely disrupted. Right? If you see that there are certain companies that are adopting to this availability of low latency, high reliability, high data rate network, and they're exploiting it to make their business case stronger, or they're using it to, make the management and operation of their factory or plant a little bit more efficient, then they will have an advantage over the others, right? So they may be in a good place to disrupt the rest of the industry. All right, so question number 3 says, China is successful in initiating 5G setup in the mid-band 3 to 4 gigahertz while continuing to improve its technology on the high band. While US carriers such as AT&T and Verizon concentrate on the high band millimeter wave. So US is falling behind on the 5G race. The answer is no, US is not falling behind on the 5G race. US is really up there. So the thing is, sometimes it's also your system and how easily you can displace your existing occupants of a certain frequency band. It might be easier in certain countries where the equivalent of your IMDA has a little bit more say in, I allocated this spectrum to you today. Tomorrow you don't have that anymore. In some other countries that may be a bit more difficult to do, so they would take a different approach. But then I don't think US is falling behind, because if you really want that high data rate, you have to go up to like 28, 30, 40 gigahertz band. Otherwise, you're not going to get really high data rates and low latency. So I don't really believe that that would be a fair comparison. Yeah. Okay, so now we have more questions. Is there a roadmap for chipset and network equipment for millimeter wave devices on a standalone 5G network architecture in 5G? All right. So as far as the network equipment and chipset manufacturers are concerned, they are going to follow the standards set aside by 3GPP, let's say. And in that case, there is not as much of a country-specific roadmap, right? So when these companies will make these chipsets, they will be standard compliant, and then they'll. So now, if you're asking whether there is a chipset manufacturer trying to do this in Singapore or not, to be honest, I'm not. It's just that I am not aware. It doesn't mean that there is or isn't, but I'm not aware of manufacturers doing this within Singapore. And has Singapore or IMDA taken non-standalone into consideration and facilitate a roadmap to transition from non-standalone to standalone? So now, I can't really speak for IMDA, but to the best of my knowledge and my understanding, they do have a plan, and they are totally cognizant of the fact that, most likely we will have to go from NSA to SA, and they would have a roadmap for going that. All right. Now, next question says 6G will eventually replace 5G. Yes, that's coming in 10 years. And but 6G is still in early research phase. Is NUS doing research on 6G? All right. So this is a very interesting question, especially for me here. Because, to be very honest with you, it's way too early to know what 6G would be like because we haven't even come to the end of 5G. The entire 5G standardization has not been done yet. So it's a bit too early to say what 6G would be. But then for us professors and our PhD students or master students, they like to do research and they have to publish papers, right? So if you put a 6G in the title of the paper, these days it's very attractive and it helps you to publish that paper. But if I were to speak really standing here and be very honest about it, when 6G comes out, let's say in 2030, the paper on 6G, the research on 6G that is done here, probably is not going to be very relevant to what it is, right? But what people do believe what 6G would be looking like is, now with 5G, we talk about IoT devices and billions of devices. And with 6G, we feel that the number of devices would scale a lot higher. And your whole spaces will be intelligent. So for example, I'm standing in a lecture theater here right now. So the space here in the lecture theater will be intelligent in the sense that it will be able to look at gestures of people and react based on that. It would be more in tune with human needs and emotions and other things. So that's probably one thing we will see in 6G. But we do research on 6G, but to be very honest, I don't know what real 6G would be like in 20 years. 10 years rather. Yeah. Do we have more? Okay. What kind of killer app do you think are lacking and may emerge soon? I think the easiest thing I can think of are, the killer app from if I was a telco, right? If I was Singtel StarHub M1, the killer app that I want, especially from a consumer, is something that will make them consume a lot of data. Right? That will get their data bill at the end of the month to be 50 GB, 60 GB, 100 GB. Then they would sign up for my 5G. Right? So what could be those? Maybe very, very high definition videos once TV networks and movie theaters start producing them. And maybe more of augmented and virtual reality applications. So that's coming from the point of view of consumers. But I think in the short term, probably the killer applications would come more from the industry that requires control loops that have very, very short time frames. Maybe something like autonomous vehicles or smart cars and things like that. So that's probably the most likely or the most killer app that will emerge the soonest.